In this next section, we'll go through what is called state retention. So the previous logic gates that we have covered all pass values from the input of the logic gate to the output as soon as the input changes. So if we have a continuous changing of our inputs, the output's going to continuously change, and we're never going to know what the correct value is at any given time if we're trying to measure some calculation, for example. So let's say we want to do an addition of two numbers. We need the inputs to stay stable in order to get stable outputs to the calculation. So in effect, we need some sort of new logic gates that can stay stable for a known or predictable period of time in order to both create stable inputs that allow the logic function to happen through all our gates, create a stable output, and then we can use those new logic gates to capture the output and retain that output for a stable period of time to do something new with that going forward. So basically the two main circuit types that we use for that are latches and flip-flops, and we'll go through that next. So there's a few different types of latches, but to begin with, I'm just going to go through the functionality of what's called a D latch. This type of latch has kind of two inputs. The main input is D, which is your data, but you also have a clock input, which is kind of a control input, similar to a select for a mux. And the clock controls whether D goes through to Q transparently or whether it doesn't go through, depending on its value. So in this case, when clock is 1, the latch is transparent, which means it allows D to go through as a buffered version to the output Q. So if D changes from 0 to 1 when clock is high, the output Q will change from 0 to 1, and vice versa. If D goes from 1 to 0, Q will go from 1 to 0 as long as clock is 1. Now when clock is 0, the latch is opaque. In other words, it doesn't allow D to go through to Q. The output of the latch does not become an unknown value or a Z value. What happens is when clock is low, the output value of Q holds whatever value it had when the clock went low. So if the value of D and Q were 0 when clock went low, then Q would stay 0 as long as clock is low. No matter what happens to D, D can transition and Q won't change as long as clock is low. So this type of latch is known as a transparent latch. In other words, it's transparent during one level of the clock and not transparent during the other level. Or also a level sensitive, as you can see, depending on the level of the clock, its behavior changes. So let's go through a real quick description of, on the lower right hand side, there's a timing diagram that kind of pictorially shows how this behaves. So you can see at the beginning, all three clock, D, and Q are all low. While clock is still low, D transitions from low to high. Nothing changes as far as Q is concerned. Since clock is low, Q stays stable, same value. Now, a little bit after that, clock goes high. So as soon as clock goes high, it now causes the latch to become transparent. And so the output will follow whatever D is. As soon as clock is 1, the output Q is dependent on the value of D. Since D is 1, the output of Q will go from 0 to 1. A little bit later, the D value goes back from 1 to 0 while clock is still high. Since clock is high, Q will follow the value of D and go from 1 to 0 as well, and then they both stay 0, and eventually clock goes low, causing Q to stay 0 because that's the value it was when clock went low. And then toward the very end, D goes back high again, but it's going high during the time when clock is low, so the output will not follow that value, because when clock is low, the latch is opaque, it holds its value. Now that we know logically how we want a D-latch to behave, let's look at how we can create the circuit that will actually create that logical function. So basically what we want to do is we either want the value of Q to equal the value of Q if clock is low, or we want the value of Q to equal the value of D if clock is high. So we can do that by using a multiplexer, a 2-to-1 multiplexer, that chooses between the current value of Q cycling back, or a new value of D if clock is high. So on the left hand side, we can see we can take a 2-to-1 mux and then just have the output of that 2-to-1 mux becomes Q. Then we can create a buffered version of Q, so Q bar, and then another inverter to create Q again, or a buffered version of Q that feeds back into the 2-to-1 mux. So this function can be actually in transistors the way that you see in the circuit on the right is kind of the lowest number of transistor count to produce that function, rather than using a 2-to-1 mux that would be, let's say, for example, the 2-to-1 tri-state inverting mux followed by an inverter, or basically we're basically here going to be using pass gates as our 2-to-1 mux. So one pass gate has clock going to the NMOS device of the pass gate for the D input to the mux, whereas the other pass gate has clock bar going to the N transistor of the pass gate for the feedback of the buffered version of Q. And so you can see what winds up happening in the circuit on the right there. If clock is high, the pass gate in the upper left that has the D input going to it has the NMOS clock is high, so the NMOS is on, clock bar is low, so the PMOS device is on, and so the D value will transfer straight through and go to Q. It will also feed through the inverter to Q bar and feed back to the other pass gate, but the other pass gate, since it has the flipped version of clock and clock bar to the other transistors, that pass gate is off, so that is not fighting or trying to drive the output Q at all. It's tri-stated. In the other version though, or when clock goes low, now the clock going to the D pass gate, or the pass gate where D input is going to turn off the pass gate that's in the upper left, and the pass gate that's in the lower part is going to turn on. And so whatever value is at Q at that point will feed back through the two inverters and be driving Q again. So it will hold its value and will not allow D to change the output value. So this slide shows maybe a little bit easier to understand version of what I just described in the last slide on the functionality of how the D latch operates. So here we have in the upper left corner, we're replacing the pass gates with basically just switches. So when clock is 1, you can see the switch that connects D to Q is turned on, and the switch that has the feedback from the buffered version of Q is open or turned off. And so when clock is 1, D flows straight through to Q. When clock is 0 on the right hand side, the D switch is open and the lower switch is closed on the feedback of the buffered version of Q. So when clock is 0, whatever value is in Q gets fed back through a buffered version and just drives Q again. So it holds whatever state, just gets held there. And again, down at the bottom, there's the same timing diagram that we saw before that can show you when clock is low, when D switches, Q does not switch. When clock goes high, Q will follow whatever value D has. So when clock first goes high, since D is high, Q goes high. Clock stays high and D goes low, Q will follow it and go low as well. And then once clock goes low, Q stays low as long as clock is low. It keeps its value no matter whether D changes or not. So in addition to latches, the next main type of state retention element is a flip-flop. So I'm going to go through one of the most basic flip-flop, which is the D flip-flop. Here I'll go through the functionality. The flip-flop is different than the latch in that it's edge sensitive as opposed to level sensitive on the clock. So we have a similar structure where we have two inputs. The D input is the main data that's going into the flop. The clock input is basically the control to the flop on whether you take the value of D or not. And the Q is the output. So in this case, rather than being a level sensitive where we let the value of D go through when clock is high or low, the functionality of a flop is it's edge sensitive. And by edge, it's sensitive to the edge of the clock when the clock transitions. So the main functionality most of the time for a D flip-flop is when the clock rises, so when the clock transitions between 0 and 1, at that point in time, that singular point, we copy the value of D into Q and we hold it until the clock transitions from 0 to 1 again. All other times, Q holds its value. So it only transitions once right at the time when the clock switches. So this is called a positive edge triggered flip-flop. If we captured the value when the clock was going from high to low rather than low to high, it would be a negative edge triggered. But this particular type, and the most common, is positive edge triggered flip-flop, and it's also called a master-slave flip-flop, and we'll get into that in the future foils. So you can see down in the bottom here, there's a timing diagram that kind of shows you graphically how this behaves. We have D and clock and Q all low to begin with. D switches, nothing happens to Q. Q stays the same value. As soon as the clock switches from low to high, the value of D at that instant is 1. So we will take that value and copy it or transition it through to Q. Q will go to 1, and it will hold that value of 1 as D keeps switching several times, and the clock also switches from high to low. Nothing happens to our value of Q. Q stays stable as long as there isn't a transition of the clock from 0 to 1. So we keep moving along to the far right side of the figure, and when clock, after it's gone low and then it's going from low to high again, we look at the value of D at that point in time. D is a 0, so it will copy that 0 value and transition Q, your output, to 0, and it will now hold that 0 value until the clock switches from 0 to 1 again over the next cycle of the clock. So now that we know the logical function of a D flip-flop, let's look at what this circuit might look like to actually create a D flip-flop. So looking at we can basically build this from two latches is the way that we can logically build a D flip-flop. So if we look at the figure on the left-hand side, lower left, if we take a two different D latches and hook them in series, but have them clocked by inverted clocks. So the first D latch that has D going into it is clocked by clock bar, and then the output of that goes into a second D latch that's clocked by clock. What that winds up giving us is when clock is high, that means clock bar is low, that first D latch is closed, so no value goes through. But when clock is low and clock bar is high, that first D latch allows the value to go through to QM. Now, as soon as when clock is low, the first latch is capturing the value of D. As soon as clock goes from low to high, it causes clock bar to go from high to low, which causes that first latch to hold the value that was at D as soon as the clock went from low to high, or clock bar went from high to low. So now QM is a stable value, and when clock went high, the second latch will open and allow QM to go through to Q. So you can see as soon as clock goes high, the value gets captured and held in the first latch, and it gets passed through the second latch, which causes that edge-triggered property to happen. Now, on the right-hand side, we'll see the actual circuit that we actually create. Instead of using, if you go back in a couple slides and look at what the D latch looked like, we had an output Q that came directly from the pass gate, and we had a Q bar that came after one inversion. And you'll see that instead of having D go to Q, or D go directly to QM, and then that going through a pass gate to Q, instead we use QM bar, and we're then going through another inverter to get Q. And this causes us to get a nice, good, strong value of Q out, rather than going through two pass gates and have a degraded value of Q going out. So this is one of the lowest number of transistors required for a D flip-flop, and so it's typically the most common that you'll see. We basically have 4 pass gates and 4 inverters, since each of them have 2 transistors each, we have 8 types of gates, 2 transistors each, 16 total transistors, which is one of the most compact designs that you can get for a D flip-flop design. So let's go through the D flip-flop operation a little bit more in a circuit diagram that might be a little bit easier to see the functionality. Again, just the main thing that we're doing here is replacing the pass gates with switches showing functionally how it works. So you can see when clock is 0, what's happening is the input to the D is the switch is closed in the master latch at the input to D, and so D goes through and goes through an inverter to QM bar, and there's no feedback loop. The feedback loop is an open circuit, and so we have D going to QM bar. The second latch, the input to that latch is not open, and so we're not capturing the value of QM bar. Instead, the feedback loop, the switch to the feedback loop of the second latch is closed, and so whatever value was previously in that latch is just being held, and the output Q is a stable value when clock is low. When clock goes from low to high, what winds up happening is the very first switch from D to the first latch opens up, and so the first latch holds a constant value. The feedback loop, the switch closes, and we now have the feedback loop is fully connected. And so QM bar will now hold a stable value of whatever was there as soon as clock went from 0 to 1. And that value of QM bar is now being fed the switch going from the first latch to the second latch is now closed, and so QM bar gets fed through an inverter to Q, and we have our output value Q. When clock went from 0 to 1, we now have QM bar going through to Q, and the feedback loop of the second latch is open, and that switch is open, so we just have QM bar going out to Q. So looking at the timing diagram down at the bottom is what we saw earlier. In effect, when clock switches from 0 to 1, it will capture the value of D right at that point when the clock switched and send it to Q, and otherwise Q stays stable until the next time clock makes the transition from 0 to 1. Again, it will capture the value of D, send it through to the output, and then it'll stay stable at that value until the next time clock switches from 0 to 1. So I'm going to take just a couple minutes to talk about one dangerous thing that can happen with your timing and your flops or sequentials, and that's what's called a race condition. So let's say we have two flops that are in series with each other back to back. So we have the input to one flop, D, goes to its output Q, and then that Q or Q1, and that output Q1 goes to another flop and creates an output Q2. Now, typically when we do something like that, we want them clocked by the same clock physically if we can. But let's say if these are separated from each other by a little bit, and so we can't have the same physical clock, but we would like those clocks to be the exact same timing to them. Now, if that was true, then when clock goes from low to high, clock 1 and clock 2 would both happen at the same time. So the first flop, the value of D would come out on Q1, and at the exact same time, the value of Q1 would come out on Q2. So if D was a 0 and Q1 was a 1, and clock goes from low to high, then the 0 at D would go to Q1 and be a 0. The 1 at Q1 would go through and now be a 1 at Q2. So we would now have a 0 at Q1 and a 1 at Q2. But let's say our clocks are not exactly timed to each other. And in this case, let's say clock 2 is actually delayed a little bit and delayed later than clock 1. What happens in this case is clock 1 switches from low to high, captures the value D and propagates it to the input of clock 2, and then since clock 2 is delayed, the clock 2, when it goes from 0 to 1, we now have the value of D sitting there, and that went through just a little bit ago, and now it gets captured in the second flop and goes straight through. So instead of D taking 2 cycles to get through to Q2, it goes through in the single cycle, and in effect we get what's called a race condition. So D raced through Q1 and Q2 all on the same edge when it should have taken 2 clock edges to do it. This is what's called a hold time failure, or sometimes also called a min delay failure, because it went through in a minimum of time quicker than it should have. So this is a type of thing that we don't want at all, and will cause a failure on our chip if we have it. So we try to design these things out as carefully as possible. So the race condition or hold time failure that we talked about in the previous slide, one of the ways to design that out is to use, instead of a single clock that goes to all of your flip-flop elements, you can have 2 clocks going to your flip-flops or your latches if you have positive and negative level latches, and those two clocks are basically out of phase with each other and non-overlapping. So the time that those each clock is high is not switching at the exact same time as you basically get a phase 1 clock and a phase 2 clock, and those go high for less than 50% of your cycle, and you make sure that there's space between the transition of phase 1 going high and phase 2 going high. So as you can see in the lower, the timing diagram for like a phase 1 and phase 2 clock is shown at the very bottom there, and how you would connect it up to your master slave D flop is shown in the circuit above, where the phase 2 clock goes to the master element, phase 1 clock goes to the slave, and by doing this type of thing you can guarantee that you won't get these race conditions as long as the overlap time, as long as you don't have too much clock skew in your design. If you get a whole bunch of clock skew, you can always get race conditions, but you try to manage clock skew really well. So in a lot of these lectures, we'll be talking about two-phase clocks. In industry, we tend to use just a single phase clock. We don't use the two-phase clocks because clocks use a lot of power. Sending 2 clocks through your entire design uses twice as much power, and that's not something that typically industry wants to do. So they wind up instead managing their clock skew really, really carefully and having timing checks that make sure that you don't get clock skew beyond what will cause these race conditions.